So, hi everyone, I'm Dennis from the University of Edinburgh. And fortunately, the initial final mass was introduced wonderfully this morning. But essentially, it's a great way to just constrain stellar models and the turbulent final stages of stellar evolution. This is one of the current best models we've got, where it's based semi-empirical. So observations find the final mass, and then we use, observations find the initial mass. I'll start again. Observations find the final mass, and then we go through a series of steps, which I'll take you through to find the initial mass. And essentially, this model only has 79 known masses of initial white dwarfs, whereas this work aims to multiply that by a few thousand, hopefully get about 5,000 total. So all our final masses are given to us by this paper, whereas the initial masses are a bit more difficult. I have to skip over how we remove spurious sources, but our data is essentially just Gaia data. So DR3, it's fantastically accurate, but there is crowding issues. So we essentially just use a neural network to remove those issues and leave ourselves a very clean, very tidy data set, but it removes many of the white dwarfs. So we use the white dwarfs from that paper and ignore our flag of spurious data there. The major challenge is actually identifying stellar clusters and with a clustering algorithm. So we want to target co-moving groups and stellar clusters within the Milky Way plane that form from a single cloud collapse event. We can then get an age of that cloud collapse that would give us an estimate of the total age of the white dwarf. And this work is based off the Constrain and Kavli paper, where they used HDV scan. You use slight differences the way we implement this. We wanted to remove any edge effects and any artifacts which have been introduced in the clustering. But the problem with clustering algorithms is they're computationally very heavy. So if you want to cluster the whole Milky Way, you need terabytes of RAM. It's non-distributed. It's just a nightmare. So we cluster our data on three-dimensional positional data and two-dimensional velocity data to try and remove some of the noise. But quite clearly, if you have objects that are physically separated but happen to move in the same direction, they're not from the same cluster. So if we separate by positional only, we can actually still get good results. And the method we introduce here is called HEADS. That stands for the Hierarchical Data Splitting and Stitching software. And this is a novel software that I've wrote, and it is published or being reviewed at the minute. And it essentially makes clustering distributed, scalable, and repeatable for any clustering algorithm. You can split on a subset of the data set of the features. So in this case, we just split on the positional data and add the velocity to the clustering only. And HEADS allows you to have these overlapping regions. It means any cluster is physically distant from any boundary. So you don't have any edge effects. And like I say, you can get it, it's scalable and people can repeat your results. And this is a snapshot of actual DR3 clustering along the Milky Way plane. And then we simply use the plot from before to stitch that back together, and we get these nice clusters. So this is the computationally difficult part. How do you actually get the physics out of this? Clearly, this is only statistical clusters. There will be some level of anomalies. It's estimated about 10 to 15% of all clusters are anomalies in this work, from literature, things like that. But there didn't really seem to be much of a consensus of how to achieve that. So we went back to the basics and just thought, what if we plot every cluster on a HR diagram? We should get the main sequence, ideally a red giant turnoff. Unlikely to get a white dwarf population with these kind of co-moving groups. But like I say, we add them in from the paper anyway. And essentially, if you have a main sequence, you have an edge detect. You can have an edge that you can detect. And edge detection lends itself to something called the Huff transformation. So in Huff space, any edge becomes a point, any point becomes a line. So the middle plot here, you can see all the lines converge is where an edge has been detected. And if you find all the edges within your image, you get a load of metrics such as the mean gradient, the standard deviation of those gradients, the width of your data. So if you take the best line and widen it, how wide does that have to be to basically contain 80% of your data? The 80% is just to account for red giant turn off, things like that. And from this, we then can use those metrics to basically train a active learning. So we have a few thousand clusters here. And the active learning stage just means you don't have to classify 1,000 groups to get an age, to get good clusters. And this is the probability of any cluster being a good cluster from that active learning. As you can see, the bottom, there's quite a clear main sequence here. Whereas if you look at the top left, the main sequence gets very fuzzy, very low population. So for this work, we're working with about the 60 to 70% stage is where we say anything below that is spurious, and anything above that is a good cluster. And if a white dwarf is in there, that's what we're interested in. And completely independently to all the literature, it's about 10% that are in that less than 60% population. So we seem to be in agreement there. So now we have our clusters, we need to find a way of aging them. I'm sure you're all aware this can be cumbersome, quite slow. If you try and do Bayesian fitting, it's computationally very difficult again, which is what we're trying to avoid, because we're trying to make this all scalable and repeatable to anyone. So we've developed a neural network to cluster these, to age these clusters, sorry. And the neural network from basically on Milky Way stellar catalog clusters and a synthetic data set from parsec models to try and just supplement the gaps in that slightly flawed data set. And these are the results we get. You can see the synthetic data as it's clean and tidy. You get very good agreement. And then the real clusters, there seems to be an issue below about 8 depth. But realistically, it's not too much of a problem for this set work because the white dwarfs haven't been formed in those clusters. The reason we think this is because the population of the turn-off point is quite low there, and these clusters only contain about 100 stars. So if there's not many stars to begin with in that area, we're not going to get the turn-off point accurately. But it shouldn't affect too much this work. So essentially we have our clusters, we've now aged them with that neural network, and we have the white dwarf cooldown models that were described in an earlier talk. And fortunately, the Fuselo paper gives us the type of star, and it gives us the surface gravity. We use the Montreal cooldown models, so we have all our pieces in place. Unfortunately, I was hoping to get this done before we got here, but as you can probably tell, the quality control is a machine learning model. We have to get that completely correct. The clustering is a machine learning model. We have to get that correct. Otherwise, errors are just stacking on top of each other. So essentially, I didn't want to publish results that were spurious, but we're hoping, like I say, to get about 5,000 white dwarfs that we have checked and are the accurate results rather than just any 5,000 white dwarfs. I've been a little bit quick, but I can go into some details and questions. Sorry. We've almost developed a scalable approach for the initial final mass relation. I should say just a few details to iron out, especially on the quality control of these cluster populations at the end. The big introduction at the minute is heads. That scalable approach is already out in the public domain. Paper should be on archive maybe this week. Ask any questions about heads, I'm more than happy to talk about that one. And yeah, we eagerly await the IFMR results as much as you do. Thank you.
Okay, plenty of time for questions.
So if the most massive white dwarfs have left the clusters and are parsecs away, maybe tens of parsecs away, would you identify them as cluster members?
No, we wouldn't, because the way we cluster is we obviously do the statistical clustering, and then with HTV scan, you get a probability of another object being a member. So we check the white dwarfs from the list. Are they part of the group? So if they're physically distant, they're gone in the data. Unfortunately, yeah.
So how do you get 5,000 white dwarfs? Looking at your diagrams, can you point out some of them? Because I could see the main sequence, but can you point out the white dwarfs in those? Like how many clusters have you identified in total?
So the number of clusters we have is about 3,000. I think that's before the quality control cut. So that's the thing with our quality control cut that we have from the data. We actually remove a lot of the white dwarfs because they're fainter, and Gaia has an issue with blue band anyway. So we've had to ignore the cut there and reintroduce them into the clustering. So these don't actually involve many white dwarfs. They're kind of separate. So I do actually have a couple of slides on the. So this is the Gaia data we have. If you just have all the data, and you have to remove the spurious sources, and we use the neural network, like I say. So you can see the spurious data actually overlaps quite a lot with the white dwarf population. This is just an issue with Gaia in itself. So yeah, that's why I had to separate them and then introduce them at the end again.
Thanks. Pretty interesting. What are you assuming about the atmospheres of the white dwarfs when you choose which cooling models to interpret them with?
Essentially, we're trusting the literature there. So it tells us if it's DA or DB type.
Sorry, you're trusting the what?
The literature. So this Fuselo paper, this one, has a list of all the white dwarfs that we use.
So that's based on the colors? Or
oh?
That's based on the colors?
I believe so, yeah.
Oh.
Yeah.
Thanks.
Hi, you're using the models from the Montreal group. Mm-hmm. Have you tried different models?
We haven't yet, because we're focused on the, making sure all the models that we've introduced are correct beforehand.
Yeah, the thing is, the atmosphere models are great, but they use the 50-50 carbon-oxygen central composition for the cooling ages, and that will change a lot depending on mass and also depending on initial metallicity. And since you're dealing with globular clusters, you expect the metallicity to change, and that will give you different central compositions for different masses.
Yeah,
I mean, that's important.
Realistically, we should use different models. That stage is quite easy in a sense because we've got our age, we've got our white dwarf. It's just applying that model and checking the results. The biggest problem is finding the ages of the clusters. So until we verify the actual errors on that, that might actually be a smaller error anyway, which model we use. So.
You disagree?
Just a clarification on one of your plots, you had a purple and yellow Rorschach plot test.
Which one, sir?
This when you're doing your clustering, you had a purple and yellow.
Oh,
and you.
This one?
No, farther back. That one.
Yeah.
What is purple and what is yellow?
Oh, this is just to try and give a bit of contrast. So
yeah, but
a yellow one, so you can sort of see. It has a laser, does it? Yeah. So that's a cluster, and then the blue one will be a different cluster. The colors are just for clarification.
Okay, I understand. Thank you.
Yeah, it wasn't a age or metallicity or anything like that.
Okay, if there are no other questions, let's thank Denise again.